After we run a regression model, we need to check whether the residuals are autocorrelated. If the answer is yes, we have an issue. The least square estimator is still a linear unbiased estimator, which means on average is still accurate. However, it is no longer best, which means the standard deviation is not the smallest. In other words, the OLS estimations are not the most precise one. The formula for the standard deviation or standard errors usually compute for the least squares are no longer correct, as we mentioned before. And we know that the standard errors are used to construct confidence intervals and to perform hypothesis tests. If they are not correct, the test result and the confidence interval estimations may be misleading. So we have an issue. We have three strategies or three estimation procedures can be used to address this issue. The first one is to run a least square estimation. However, we use an alternative standard errors to correct the bias. We call that heteroscedasticity and autocorrelation consistent standard errors. That's an recognition that if we have serial autocorrelation in our error terms, we have both heteroscedasticity and autocorrelation, then we need to estimate a standard error that can be robust to these two issues, and we use them to perform the test. So this is the first approach. The second one is to estimate an AR model by using nonlinear least square methods. So that based on the assumption that the error term has a first order autocorrelation as specified on the slide. The last one is to estimate an autoregressive distributed lag model or ARDL model. So we're going to go through those three strategies one by one. The first one is to still use OLS, but use a heteroscedasticity and autocorrelation consistent standard error. So we estimate this linear regression model by using OLS and find out that the residual terms is serially correlated. Then we need to request this standard error from the software. I wouldn't recommend you to calculate it manually. That's just not worth your time. And if you are interested in the formulas behind the standard error, those are the formulas that you may use, and you can also find them from our textbook. The idea is we recognize that the error terms are serially autocorrelated. Basically, we have a formula to calculate, to capture this autocorrelation problem. Then based on that formula, we correct the standard error accordingly. Then we use the corrected standard error, and we call them HAC standard error. So we use software to do this, sort of tedious, but if you have a decent software like Stata, it's not a problem to request that standard error. On this slide, I give you two sets of outputs. For the same linear regression model, the first line, those are LS standard errors, that's from OLS. The second one is based on this HAC standard errors, which are heteroscedasticity and autocorrelation consistent. They are not affected by these two issues. So we notice that the correlation coefficients are the same. I didn't change them. The software won't change them. The procedure only gives you different standard errors. And based on those different sets of standard errors, we have two sets of t-tests to check whether beta 2 or the coefficient of unemployment rate changes is significant or not. So based on OLS, the test statistics is minus 2.301. The p-value is less than 5%. However, if we use the HAC standard errors, the p-value actually is over 5% and is nearly 10%, which means the OLS standard errors give us misleading test result, given the presence of autocorrelation in the residual term. So we should use the HAC standard errors, and that's the test result. The second approach is to use a nonlinear least square method. but with an AR1 error specification for the error term, which means we assume that there's only one period lag effect in the error term, and that is controlled for by rho, that's the correlation coefficient between ET and ET minus 1. So rho is essentially is the first order autocorrelation coefficient for the residual term. It can be estimated using this formula, and we are not unfamiliar with this because this is just a standard equation to calculate the correlation between two variables. And in this case, the two variables are ET and its own one period lagged term, ET minus 1. If this relationship holds true, which means the effect of lagged term of ET lasts only for one period, over the entire time period, if we would like to calculate the correlation between any two error terms that are k periods apart, we can make use of this relationship. And based on those calculations, we can calculate rho k actually is the case order of rho. So this is actually an example to demonstrate why on previous slides, we call this rho or this coefficient multiplier. So that's actually is an effect of a multiplication over the long time. Okay, if this relationship holds true, we have a AR1 error specification. The regression model can be rearranged into this. So essentially, we insert ET into this equation. Once we insert ET into this regression model, we can rearrange it. So we have a intercept term that's actually a combination of beta 1 and rho. We also have a coefficients corresponding to each one of those independent variables in this regression model. However, it is clearly not a linear function of the parameters. The parameters are beta 1, beta 2, and rho. Those are the three parameters we want to estimate. That is clearly not a linear function. So for example, over there, that's a product of two coefficients and xt minus 1, which means xt minus 1 is not linearly related to yt. So we are not able to estimate this regression model by the standard OLF method. Instead, we use a nonlinear least square method. So it uses iterative generalized least square estimator. And in this course, we use this Cochrane all-cut procedure, which is one of those most commonly used procedure in the softwares. Usually, if their data is of good, reasonable quality, those procedure will not give you distinctively different result. So this procedure is fine. And with this procedure, we still use Phillips curve as an example, and we can estimate the nonlinear LS parameters are 0.7609 for the intercept term and 0.6944 for the coefficient of DU. And we can also estimate what the value of rho is. It has a standard deviation as a 0.09. So we can make a comparison between this nonlinear estimation and the two sets of regression outputs we obtained on previous slides. So the first one is the OLS standard estimation. And the second one is the heteroscedasticity and autocorrelation consistent standard error. And the third one is this nonlinear estimation. Okay, the benefit of using this is we actually have an estimated value of rho and its standard deviation. You may notice that it is significant, which means our specification is correct. And you may notice that the coefficients are different from the previous estimation simply because we are now using nonlinear LS estimation method now. Despite the fact that the coefficient estimates are slightly different, the standard deviation from nonlinear LS estimates are smaller. So we conclude that the nonlinear estimates are more accurate. All else being equal, we would like to have a standard deviation as smaller as possible. That's the deviation between our estimate and the true parameter value. So the smaller the better. On that note, nonlinear LS is better than the other two estimates. It's more accurate. The third approach is this autoregressive distributed lag model, ARDL model. this equation is the one that we used in the nonlinear LS estimation on the previous slides. You may notice that it is essentially the same as this one. We just use different notation. And you may notice that we actually, even if at a first glance, it looks like we have 4 parameters to be estimated, delta, theta 1, and delta 1. However, essentially, we have just only 3 coefficients to be estimated. This is because the coefficient corresponding to xt minus 1 is the combination of theta 1 and delta 0 over there. So we only need to estimate delta, theta 1, and theta 0. Once we have those 3 values, we have delta 1 already. So this model can be estimated with a restricted LS method, which means it's still this square, but with a restriction, or the constraint is over there with this constraint. That reduced the number of parameters from 4 to 3. They are still equivalent. And as long as this assumption that restriction is valid, the LS estimation is valid. The nice thing about this approach is we have the data to check whether this restriction is valid or not. So we have a test available. Okay, let's use the Phillips curves example again. And we estimate this ARDL formula over there. So we have a correlation coefficient and standard deviation given on the slide. Use this restricted LS estimate. We also have a walk test statistics to check whether the constraint is supported by the data or not. So for the interest of time, we're not going to go through the technical details of this test. But the essence of it is with the data, it can check whether the pattern it derived from data is consistent with this restriction or whether it's supported or not. And we do not reject the null hypothesis, which means the assumption is valid that supports the estimation of this model in such a way. And once you have this, you can go step further by improving your models by removing this DUT minus 1, which is insignificant, to further improve your model. Technically, from a technical perspective, we always want to have a model with a significant variable only. So just as an illustration, you can remove this insignificant term and re-estimate the model. It's quite flexible. The model will pass the test, and the coefficient now is significant. On this slide, I put the results of the 3 approaches side by side to facilitate comparison. So we started with this linear regression model, yt equals beta 1 plus beta 2 xt plus this error term. After estimating this regression model using OLS, we noticed that the error terms suffer from autocorrelation. Specifically, we have an AR1 process as specified by this equation. To address this issue, the first approach that we can use is the LS model with the HAC standard error. Specifically, we still use the correlation coefficient, coefficient estimates from OLS estimation. However, we use a different set of standard error to perform the test. And the standard errors are heteroscedasticity and autocorrelation consistent. So the coefficient estimates, this 0.7776 and negative 0.5279 are the same with OLS estimation, but the standard errors in brackets are different. So those are HAC standard error. They are more reliable compared with the OLS standard deviation, but the limitation of this approach is we have no idea what the value of beta is. We just recognize, oh, there's some autocorrelation issue in the error term, but we do not explicitly model this rho or this correlation coefficient in the estimation process. And as a result, we are not able to perform a test to check whether the autocorrelation is significant or not. The second approach took that issue into consideration. So we have this linear regression model. We also have this specific AR1 procedure. What we did was to insert this equation into the linear regression model to recognize this AR1 process. Then we use a nonlinear LS model to estimate this one, simply because after we make this kind of manipulation or changes, the relationship between xt and yt is not linear anymore. So we use a nonlinear LS method. We use this iterative generalized LS method to estimate both the coefficients and the standard deviation. On top of that, we explicitly estimate the value of rho and the standard deviation, so we can check whether AR1 is significant or not. As a result, you may notice that both the standard deviations and the coefficient estimates are different between the first and the second sets of results. The third one is similar to nonlinear LS model. It's just the estimation process is different. We call it ARDL model simply because we have the lag terms of both the dependent variable and independent variable in our regression model. And by imposing a constraint, which is a result of this AR1 process, we can estimate those betas and the rho, and we can also check whether the AR1 process is significant or not. You may notice that the correlation, the coefficient estimates are quite similar between these two sets. It's simply because the estimation process and the specificational assumptions are very similar between those two. Also, the test result for rho are quite similar as well. You may also notice that we do not have a standard deviation for beta 1. This is because the value of beta 1 is derived based on the restriction that we imposed. So it's not directly estimated from the model, but that is not an issue because beta 1 here in this regression model, that's our constant term. When we estimate a regression model like this, we are interested in the value of beta 2, which reflects the relationship between y and x. We may also be interested in the value of rho. That's the nature of the autocorrelation process. But the constant usually is not a concern. So I wouldn't call it a limitation. So as a result, nonlinear LS model and ARDL model are more commonly used in practice. Between those two, if you have an AR1 process, there isn't much difference between those two. But if you have a higher order autocorrelation process, you may find the ARDL model more helpful. So we're going to have a conversation about how to estimate ARDL model in general, not just restricted to AR1 process.